Hi, welcome to page 2 of our of section 5.1. And two other quick formulas. If you want to find the period of motion, the time it takes a mass to go through one cycle of motion, that's found by just taking 2 pi and dividing it by omega. And the frequency of motion can be found by doing the reciprocal of our period of motion, which is omega divided by 2 pi. And that's just the number of cycles completed each second. Again, because you have the spring going, it's going to be going up and down. The resulting particular solution or response is the equation of motion. So here we have an example 1, and the first thing that we're going to be finding is going to be our x of t. So a mass weighing 20 pounds stretches a spring 6 inches. The mass is initially released from rest from a point 6 inches below the equilibrium position. So the first thing we need to do is we notice that our weight is in pounds. So we want to find our mass. So we go back to our equation. Our weight is equal to mass times the pull of gravity. Because the weight's in pounds, our G is going to be 32. Not just because it's in pounds, but also because we're dealing in 6 inches, which is going to be half a foot. And so we're dealing with 32 feet per second squared. That's our pull of gravity. So M is equal to 20 over 32, which is equal to, because our weight is 20, so our mass is just 5 over 8 slugs. The reason why we're using slugs is because we're in feet. So our spring is 6 inches. It's stretching our spring 6 inches. So because it's stretching our spring 6 inches, we're able to find our constant K by using Hooke's law. The force that it's applied is going to be the 20 pounds. That's equal to K times S, our displacement from, or the stretching of our spring, which is 6 inches, which is going to turn into half a foot because we're measuring everything in feet. And so our K value is going to be 40 because we're just going to multiply. Now, this x of 0 equals 1/2. This is taken from the fact that when we start, the mass is initially released from rest from a point 6 inches below the equilibrium position. Because we're 6 inches below, that is a positive 1/2, and this is where we start. So we're starting everything 6 inches below the equilibrium point. So 6 inches is half a foot, so it's a half. For x prime 0, our initial velocity, it says we're doing this from rest, so our initial velocity is 0. And now we're going to plug this into our second order differential equation, which is mass times our second derivative, which is equal to negative kx. We know all those values. Negative k is 40, or k is 40. Our mass is going to be 5 over 8. Now, what we can do is we can go ahead and just plug it into our form, our last form, which is going to be the second derivative plus omega squared x equals 0. Now, to find omega, remember, omega squared is just k divided by the mass, so 40 divided by 5 over 8 is going to be 64. So our omega squared is 64. That means our omega is just 8, in which that will come into play at the very end. So here is our second order differential equation. And based off of this information, we can go back to our initial position, our position formula for this case, which is this x of t is equal to c sub 1 cosine of wt plus c sub 2 sine of wt. Well, I'm sorry, not w, but omega. We know what omega is. Omega is 8, so we can substitute that in, and we have our x sub t, to where all we need to do is find our c sub 1 and our c sub 2. Now, to find our c sub 1 and c sub 2, we're going to use our initial position and our initial velocity. And when we plug in our initial position, we're going to, into our formula, what we get is 1/2 is equal to c sub 1 cosine of 0 plus c sub 2 sine of 0, which is just going to be 1/2 is equal to c sub 1. And then we take the derivative of our x of t. When we take the derivative, we get negative 8 c sub 1 sine of 8t plus 8 c sub 2 cosine of 8t. We plug it in, we use our initial velocity to plug in, so it's going to be 0 is equal to negative 8 times 1. We can put our 1/2 in for c sub 1 because we know that sine of 0, so this is all going to go away, and we're just left with 8 times c sub 2 times 1. So 0 equals 8 times c sub 2. That means c sub 2 is going to be 0. Because c sub 2 is 0, we plug everything into our original equation, and this is what we get. X of t is equal to 1/2 cosine 8t. Now, the first thing we want to do is we want to find the position of the mass at the times t equals pi over 12, pi over 8, pi over 6, pi over 4, 9, pi over 32. So all we're doing is we're just plugging in for t all of these values. So here I have them in the notes, and I'm not going to make you sit through all of them because you're just substituting them in and seeing what you get. So here I just have the first one. So we wanted to find the position at time t equals pi over 12. So when we plug that in, we get 1/2 cosine 8 times pi over 12. Well, that 8 pi over 12 reduces to just 2 pi over 3, so 1/2 cosine 2 pi over 3. Well, cosine 2 pi over 3 is negative 1/2, so 1/2 times negative 1/2 is equal to negative 1/4. And here you see that when we plug in x for t pi over 8, our position is negative 1/2. When t is pi over 6, our position is negative 1/4. When t is pi over 4, our position is 1/2. And when t is 9 pi over 32, our position is the square root of 2 over 4. Now, for b, what we want to do is what is the velocity of the mass when t equals 3 pi over 16 seconds? And so, in which direction is the mass heading at this instant? So what we're going to do is we're just going to take the derivative to find the velocity. So the derivative of our position function is going to be x prime of t is equal to negative 4 sine of 8t. We're going to substitute in our time now, which is 3 pi over 16. When we plug that in, we're going to get 4 feet per second. Now, because that is positive, all right, the direction, in which direction is the mass heading at this instant? Let me make sure before I say the wrong thing. It is heading downward because it is positive. If that was negative, it would be heading upward. But because it's positive, it's heading downward. All right, the last one for C, x of t equals 0. At what time does the mass pass through the equilibrium position? So our equilibrium position is when our position is at 0. So when x of t is equal to 0. All we would need to do to solve for that is to set our function equal to 0, solve for t. 1/2 cancels out, so cosine of 8t. Take the inverse of cosine of both of those. We're going to get 0, and then 8t, inverse cosine of 0 is pi over 2. It's also 3 pi over 2, 5 pi over 2, and so on. So we're just going to stick with pi over 2, and we get t equals pi over 16. So that's the time when our spring will go hit the equilibrium position. So in order to do all cases, what we did was we made sure that we're making sure that we cross all our time frames. So that's why we have this 2n plus 1 pi over 16, so that when we substitute in our 0, 1, 2, we're always going to be getting a moment in time where our position will always hit 0. So the first one, 0, is just going to be pi over 16, which we found. The next one's going to be 2 plus 1, which is 3. So 3 pi over 16 would be the next time. We substitute, we plug that in, and you see that we'll be back at 0 for cosine. The reason why it's 2n plus 1, the reason why the 2 is there is because it was always going to be 8 divided by 16. And when you have 8 divided by 16, that's going to be, 1/2 pi over 2. So the amount that it's going to take to do a period would be 2. And at the end, you'll see an example of why that's going to change based off of that coefficient with the t and whatever we're dealing with.